The Autodesk Inventor assembly environment has a number of different ways to connect components together and maintain those relationships through changes to the geometry or configuration of the assembly. The most basic of these, and the one that is used most often, is the constraint tools. In the Relationships panel on the Assemble toolbar, you can start the Constraint tool and see a number of different constraints. The first is Mate, then Angle, Tangent, Insert, and Symmetry. These constraints can also have more than one solution, allowing the user incredible flexibility in applying constraints. Beyond assembly constraints, there are motion, transitional, and constraint sets. In this lesson, we'll use a few of these, but know that understanding how to read the dialog box, applying one type of constraint, will translate very well to translating just about any type of constraint. We'll start out with an insert constraint. The insert constraint is a hybrid connecting faces and the center line of curved geometry. I'll select the inside top edge of this boss. Then select the mating edge on the hydraulic motor. This will relocate the clevis part and roughly position it. Taking a look at the top, I can see that there's some misalignment. I can use another mate constraint, connecting the axes of the two holes to align it. Now zooming around, I need to apply some additional constraints. This pin needs to go into the hole. To do this, there's several different approaches I can take, including starting the insert constraint. However, holding the Alt key, I can grab the curved edge of the underside of the pin and drag it onto the curved edge of the boss. This will inherently place an insert constraint. Another, more automated way of working with constraints is the idea of eye mates. Clicking on this part, I'll see an icon near this hole. It is an insert eye mate. It is one half of an insert constraint. By holding the Alt key and clicking on that eye mate, other eye mates will highlight in the assembly. I can drag until it highlights and connect it to that other eye mate. Right now, this component is out of position. I'll right-click on it and use the free rotate tool to rotate that component around into a better position. Clicking and dragging slightly will reconnect it to the assembly in a better orientation. Now I can apply another constraint, once again grabbing the center line and then selecting the center line of the pin or the boss the pin passes through. Now this component is locked into place. In the browser, I have two components that have their visibility turned off. I'll turn those on. I want to take the same basic type of geometry and use two different systems to define its location. I'll use a constraint once again, and this time apply a mate constraint between the inside of this face and the bottom of the claw. I'll apply that. Use a flush constraint between the top of the tooth and the face on the claw. Finally, after applying, I'll use a mate constraint again on the outside face of the claw and the inside face of the tooth. Those three constraints have located the tooth. The other primary system inside of Autodesk Inventor for connecting components is joint. Joint works on a different way of approaching things. The joint can apply different types of connection, each removing different levels of degrees of freedom based on origin points. So rather than strictly picking faces or edges or curved edges, if I hover over a face, I can see any given face has 9 different locations. The center point, or the centroid of the face, the midpoint of any edge, any given point, such as the middle of this edge, can have 3 different orientations. So right now, the normal of this orientation is perpendicular to this face, or aligned to this edge, or perpendicular to this face. So selecting the same point can give you different results. I'll select the centroid of this face, and then find the centroid of the face on the claw. Clicking, it will assume I want a rigid joint. However, I can change the joint type to be rotational, to be cylindrical, or even a ball joint. In this case, rigid is the best choice, so I'll choose that. You have the option to realign if necessary, but for this relationship, this works perfectly. I'll click OK, and it attaches. Now, at this point, the joint tool might seem much easier and much more friendly and much better to use than the constraint tool, but they have different purposes and they have different functions. It takes time and experience to understand which one works best for you. I want to open up the actuator subassembly that's used in this design. Selecting the actuator stroke constraint, I want to right-click and edit the constraint. Rather than just simply being offset 0 millimeters, I'll say 3 inches. But I can also choose to go to the next level. I can say that I want to engage a maximum offset at 6.5 inches and a minimum offset of 0. When I click OK, I can now grab the arm and move it from 6.5 inches down to 0. So this will give my actuator a range of motion. This allows you to model what the physical limitations are on a mechanism. By making this adjustment in the subassembly, the top level assembly also becomes flexible along that range of motion. We can move the claw, but no farther than that 6.5 inch stroke length back to 0. So now we can evaluate the range of motion of the design. We need to place one other item into the assembly. We'll place the crusher mounting assembly into the design, and this time we'll use a slightly different way of constraining. Starting the constraint tools, we'll go to the constraint set. Under the crusher mounting, we have a UCS. This UCS has been placed in the design and does not have to necessarily align with the standard XY, YZ, and ZX planes. It can be its own entity and it can be used for a constraint set. I'll select this UCS, then expand the hydraulic motor, and see it too has a UCS predefined. By clicking OK, it will automatically locate that design.